an oldie but goodie here. This has probably been proved hundreds of thousands, if not millions of times around the world in number theory classrooms. But I think the purity of the proof is something to behold, and I want to prove it for y'all. Now, we're supposed to show that any natural number n greater than or equal to 2 has a prime divisor. 1's not considered prime by convention. Now, I've seen it done 2 or 3 different ways, but I like this way in particular. What we do is we define a set of positive integers or natural numbers. Positive integers and natural numbers mean the same thing, such that any member D is a divisor of n. We want to make D be strictly greater than 1 and strictly less than n. Okay. Now, so it proceeds very nicely. A set is either empty or not empty. So if S is empty, then the only divisors of n would be 1 and n. That is, n would be written as the product of 1 times n. And that's literally the definition of what we mean by prime number, right? Okay. So it's supposed to be a dot right there. And of course, that means it's a prime number. Okay, it's prime. Call it P1. Okay. Now, so this first case is what they call trivial. Now, if S is not empty, then it has a least natural number. That's sometimes called the well ordering principle, the least integer principle of any non-empty set of positive natural numbers. Now, if L were prime, we would be done, okay? Because it would be that would be the prime divisor. But we're going to assume it's not L just to make it worth working here. Now, if L is not prime, that means it's composite and it has a divisor. It has a divisor greater than 1 and less than L. That's what it means for something to be composite or not prime. Okay. Now, M is a member of S, and that's I didn't write down the reason, but we know just L would be a divisor of L has a divisor. M, we can write it like this if you want. We can write like this. We know that M divides L. Y'all use the vertical slash right here. And we also know that L divides N, right? And division is what they call transitive, okay? If M is a factor of L and L is a factor of N, that means that M would that would imply that M divides N, right? You see, that would be a contradiction. That would be a contradiction since L is supposed to be the smallest. L is supposed to be the smallest integer with that property. And right here we have M less than L. So this is a contradiction. And what assumption did we make? We assumed that it was not prime. Okay, we assumed that this was not prime right up here. So, and we reached a contradiction. Therefore, L is prime. L must be prime. I've written that down right here for you. And that completes the proof. The least integer is the prime factor of N. Okay, the least integer principle or the well-ordering principle. Now, to make this slightly more concrete, let's just do the special case here, N equals 45. Okay, N equals 45. What's, I guess, could be considered difficult about the proof that you just saw is that it's abstract in the sense you're never using any known numerical values. You're just dealing with the properties of divisibility and ordering. Now, so S, the set S here, let me write S equals the set we're talking about. Okay, it's only made up of divisors greater than 1 and less than N. So you can't have 1 in this set, but 3 is certainly a divisor of 45. 5 is a divisor of 45. I'm just going in ascending order, ladies and gentlemen. So this is 5, 9, and 15. And I believe that's got to do it, doesn't it? So this would be the S for this concrete example of N. But notice that we do have a prime divisor as the least element. So all this does right above is prove this for an arbitrary N. This is a concrete case. Hope you guys enjoyed.